Hey everyone, Morgan here. So, we're going to be talking about reaction mechanisms and energy and all that today. It is the second part of the kinetics chapter. Back in the first part, we go back to that original definition. Chemical kinetics is the study of the rates and mechanisms of chemical reactions. So, we've covered rates now, and you're all good at that. So it's time to move on into mechanisms. And the two will tie together. Don't worry, rates aren't going anywhere. So we're going to start off with these energy profiles, much like the ones we did last year. So this should be kind of a review. We're going to look at an exothermic reaction. And in general, the profile for an exothermic reaction will look something like this. We're plotting time down there. We're plotting energy here. Although I have heard this called a lot of things. Reaction progress, reaction coordinate, reactants turning into products. It's always, it's time. It's just progress. Okay, so with that drawn, these are the reactants and these are the products. Up here at the top of the energy barrier is the transition state. Okay? Now, the energy difference between the reactants and the products is delta H. That's the enthalpy change. And the difference between the reactants and the transition state is the activation energy, or E sub A. Now, in this case, this releases heat. This is an exothermic reaction. Delta H naught equals a negative number. Okay? So, how would an endothermic plot look different? Energy, time, and the difference now is just that the products end with more energy than the reactants. The difference between the reactants and the products is still delta H. It's positive this time. And the difference from the reactants and the top of the energy barrier is still the activation energy. Okay? Now, there is a very common misconception in these, and that is that the activation energy of an endothermic reaction is greater than that of an exothermic reaction. And that is not true. Okay, absolutely not true. It could be greater, it could be less. It's just the way I happen to have drawn it now. Okay? So please understand that. This might be big, this might be small. Okay, so those hopefully are somewhat review. The transition state up here at the top of the barrier, sometimes called the activated complex. The arrangement of atoms found at the top of the energy barrier. Is transition state the exact same thing as activated complex? Basically, yes. In slightly more technical terms, we say the activated complex is very high energy, and a transition state might not be that as high of an energy. That's all. We use them almost interchangeably. Now, the activation energy. The activation energy is the minimum. Sorry, I misspelled that. Minimum energy required for a reaction to happen. Ion for a reaction to happen. All right, so when you have your collision of your two species, remember from last year, they have to hit hard enough, They have to hit with the right orientation. And the activation energy is you have to hit hard enough. Otherwise, they just bounce off of each other and nothing actually happens in the reaction. Okay, so that's pretty much it for page 8. Let's move on now to page 9 and start to get into the real depths of the idea of reaction mechanisms. So what is a reaction mechanism? The series of elementary steps by which a reactant is converted to a product. All right, we're going to introduce some new vocabulary there with elementary step. Now, for a reaction mechanism to be plausible, it must adhere to 2 restrictions. The elementary steps must add up to give the overall balanced chemical equation. That's the first restriction. The second restriction is it must agree with the experimentally determined rate law. If either of those are not met, the reaction mechanism that is being proposed, it's just not going to be correct. All right? It's not reasonable. Okay, what might this look like? Well, actually, it can be really silly simple. A turns into B. B turns into C. There you go. That's a 2-step mechanism. The B's would cancel, and the overall balanced equation would be A turns into C. A is the reactant, C is the product. What does that make B? B is an intermediate, a species. Neither reactant nor product that is produced and consumed in a chemical reaction. Okay, that would be B. It's produced, it's consumed, that's it. So, the elementary steps. That's an elementary step, and that's an elementary step. It is a reaction whose rate law can be written from its stoichiometry. Or some people would say from its molecularity. Now that goes against everything I talked about on the first pages of this outline. I said you can't just look at a balanced chemical equation and determine a rate law. And that is still true. The difference today is that we're not looking at the overall balanced equation. We're looking at the slowest step in the mechanism, which is an elementary step. Okay? We'll come back and we'll look at that some more and some more. Molecularity. That's just the number of species that must collide to produce the reaction indicated. Okay? Now, if it's only one species involved, it's unimolecular. If it's two species, it's bimolecular. If it's three species, it's termolecular. Just use your language skills. These are really uncommon. These are very rare. Because the likelihood of three things all colliding at the same time with the correct orientation, that's just, it's out there. It's just not bloody likely to happen. Okay, move on to page 10 now and talk about the rate determining step. This is the slowest step in a reaction mechanism. Let's talk about this for a second. My apologies to any vegetarians or vegans who are watching this video, but we're going to talk about a place out here in California called In-N-Out Burger. And all my students are really familiar with it. Amazing hamburgers. I realize I'm going to probably get some negative comments in the comment section below this video, but I'm going to say they're infinitely better than Shake Shack. Now, if you go in and you watch them at In-N-Out, the kitchen's out in the open, you can see them assembling burger. And these people are artists. Man, they really know how to put them burgers together. And they can take that patty and have that hamburger assembled in less than a minute. Thing is, every time I go in, I end up having to wait at least 20 minutes to get my lunch. What's going on here? Well, they can assemble burgers really fast, but they can't cook the hamburger patty really fast. That still takes 10 minutes. That's the slowest step in this process or this mechanism. So that is what we would call the rate determining step. Okay, now we're going to have two examples where step one is the slowest step in the reaction, or when a subsequent step is the slowest step. When it's step one, it's really straightforward. This example's in just about every chemistry book I've ever looked at. 2NO plus 2H2 gives me N2 and 2H2O. We have an experimentally determined rate law. It's correct because it's experimentally determined. And it shows 2 NOs for 1 H2, although the stoichiometry shows me 2 NOs for 2 H2. But we don't look at an overall balanced equation, so that's fine. Now here's a proposed mechanism. 2NO plus H2 gives me N2 and H2O2. Interesting. Slow step. Rate determining step. H2O2 plus H2 gives me 2H2O. So, if I add those two together, the H2O2's cancel, and I get 2NO gas plus 2H2 gas gives me N2 gas and 2H2O gas, and it matches the overall balanced equation. Now, the other restriction, does the rate law match? Well, the rate law has to be written for the slowest step. And in this slowest step, I have 2 NOs, that matches the 2 up there, and 1 H2, and that matches the 1 up there. So this agrees with experiment, and the equations add up to give you the overall balanced equation. So the molecularity, or the stoichiometry, of the overall balanced equation doesn't match the rate law, and that's cool. But the rate law does match the molecularity of the elementary step in the mechanism that determines the overall rate. So yay, that works. Now, what if it's not the first step? What if the rate determining step is a subsequent step? We have to use something called the steady state approximation. And this is relatively new to the AP Chem curriculum. Now, we looked at this reaction with hydroxide as a catalyst back on page 3. And we determined the experimentally determined rate law was found to be K times I minus times OCl minus times OH minus, which was raised to the -1. Now, what does it mean if you have a -1 exponent? means it slows it down. Increasing concentration of that species will actually slow down the reaction, because the rate law can also be written as K times the concentration of I minus times the concentration of OCl minus divided by the concentration of OH minus. That's important to keep track of. Okay? So we established this back on page 3. Now, there is a proposed mechanism for this where the first step of the reaction is not the slowest step, but it actually is in a subsequent step. Let's turn to page number 10. And here is the proposed mechanism. The first step is a very fast equilibrium. The second step is slow. That's the rate determining step. Now, I'm going to say that the rate law must be written for the rate determining step. Well, since there's so many steps, K for the first reaction, we'll call K1. Rate constant for the first one's K1. And we'd have a K2. And we'd have a K3. If we wanted to, we could even say K for the reverse step is K negative 1, because it is an equilibrium. So based on this, the rate law should be R equals K2 times the concentration of I minus times the concentration of HOCl. Now that does not match my experimentally determined rate law. But hold on. I'll prove to you that it does. HOCl is not a reactant. It's a product and then it's a reactant. Again, that's an intermediate. Okay? So I can't control the concentration of HOCl to control the rate. So something funky must be going on here. Okay? Well, since it's an equilibrium, I can write an equilibrium constant. Capital K EQ, remember these are all lowercase case, capital K EQ for that equilibrium equals the concentration of HOCl times the concentration of OH minus divided by the concentration of OCl minus. Equilibrium constants were the last thing we did last year before we went into the shutdown. Okay? Now I'm going to rearrange this and solve for the HOCl. It's going to equal KEQ times OCl minus divided by OH minus. Now what I'm going to end up doing is actually plugging this in to the rate law here, the HOCl substitution. So my rate equals K2 times the OCl, times the I minus times KEQ times OCl minus divided by OH minus. Now, let's see. I've got two constants here. They're two constants. Let's make them one constant. We'll call it K observed equals K2 times K EQ. So that equals K observed times I minus times OCl minus, all divided by OH minus. Now it turns out that is the rate law I discovered on page number 3. I've got a constant times I minus times OCl minus divided by OH minus. So this is, in a sense, the correct rate law. It's just that I can't control the HOCl, so I end up doing it down here. Okay? So, does this match the data? Yes. Check. Does this give the overall balanced equation? I can check that out real fast. Let's see here. So, HOCl's cancel. OH minus cancels. HOI cancels. Okay. Then what else else do I have? Oh, H2O's cancel. So I have OCl minus plus I minus. I said the hydroxide was just a catalyst. And then I get Cl minus plus OI minus. And it matches. Yes. Okay. So I meet the restrictions. That is a plausible mechanism. And this substitution gets called the steady state approximation. Why? Well, what we're going to assume is that since this happens so fast, as soon as the HOCl's form, they could react here. And if I react one away, before I even notice it, this fast equilibrium has generated another one. So essentially, the concentration of HOCl stays in a steady state, which is not equal to 0, but equal to some number. Okay? And they do ask you often to look at one of these mechanisms and see if it is consistent with a rate law. So you'd have to do these substitutions to see that it works out the same. Okay, that's our little tour through mechanisms. Hope you enjoyed it. Study up. This is Morgan signing off.